Okay, let's see some examples. Here's our first example, butan-2-amine. Start this way. This is our molecule. So how does this information, this is our mass spectrum. It's very different in appearance relative to the infrared spectrum. How does this mass spectrum give us insight to this molecule? Well, the most important thing we typically get is the molecular weight. So what happens? This molecule goes into the mass spectrometer. We're going to lose an electron, and we're going to lose an electron out of that lone pair. So this is our parent ion. It's our parent molecule that has now lost an electron and it's now a radical cation. We will typically see indication of this molecule in the mass spectrum, or this, not this molecule, this ion. And so butan-2-amine has a molecular weight of 73 grams per mole. So we should see a peak in here at 73. It is tiny, but that is our peak at 73. That is the parent ion. So typically, we will look for the peak that has the highest MZ value, that's mass to charge, mass divided by charge. And since charge is going to be +1 for us, this simply reduces to just being the mass of our structure. What's the mass of our parent ion? It is 73. Now, where does fragmentation occur in our molecule? Well, it occurs around, let me get my positive charge in here, it occurs around this radical. So what you typically will see is that find your radical, an atom attached to your radical, that's the alpha position, and we will break off things from the alpha atom. So what's one thing we'll lose? Well, we can lose a CH3 group. And sure enough, 73 less a mass of 15 is 58. We have a peak at 58. That is our parent ion that loses a fragment. It loses a fragment that weighs 15. What else can we see? 73, our parent ion, could also have this bond broken. This is now 2 carbons. It's an ethyl group. What does an ethyl group weigh? Well, an ethyl group weighs a CH2 and a CH3. What's the mass of a CH3-CH2 group? That has a mass of 29. So 73, take away 29, what is that, 4. 4 has a mass, oh, it's written right here, MZ of 44, and we do see, in fact, that's our biggest peak in the whole thing, is 44. So yeah, we do see signs of these types of fragmentations. We're seeing loss of a methyl group, which is going to be close to the cation and the radical. We're seeing loss of an ethyl group. So this mass spectrum fits what we would expect to see based on our structure, butan-2-amine. So very often we're going to use the mass spec. Once we think we know the structure, we're going to use the mass spec just to confirm, yeah, the mass spec is consistent with our structure. Note there are other peaks here that we're not trying to explain. This would be kind of like going up out in the nighttime sky and looking up at the stars and saying, hey, that's I know what star that is. And someone would say, well, there are lots of stars. Tell me what all the other stars are. Crying out loud, no one knows what all the stars are. So the mass spec has information in it. A lot of these peaks, we're not going to worry about those. We're only going to worry about the ones that are consistent with our structure to make sure that things seem right. And if they seem right, that's confirmation that we've done our structure properly. Let's do one more structure here kind of quickly because I talked too long in this one. This is pentan-2-all. Here's our structure, our parent ion. Let's draw on a lone pair. We're going to pull out an electron from that lone pair. That is our parent ion. If you go through the formula, you will find that's an 88, and man, is this tiny. But that's our highest peak, biggest peak, highest value for M to Z ratio has an 88. Now, if this is our radical, the atom next door is our alpha position, and so our most common fragments are going to involve breaking bonds to the alpha position relative to our radical. So one of those is a CH3. A CH3 has a mass of 15. 88 minus 15 gives us, what is that, a 73? And sure enough, we do. We see a 73. So that is consistent with what we'd expect our molecular structure to be. We could also break off this whole piece. This is a CH3, CH2, CH2. That has a mass of 43 if you add up all the atoms. 88 take away 43 gives us 45. That is our biggest peak. We'll call the biggest peak in our spectrum, we call that the base peak. It's the most intense peak. It's a relative intensity. It will always have a intensity value of 100. So yeah, this structure is consistent. Again, there are other peaks in here. We're not going to worry about all these. We can maybe explain some, but not all. So we're just going to look for basically what we call the alpha cleavage. And that's when we look for the radical cation. The next door atom is the alpha, and then we're going to break things off that alpha position. So those are some of the basics of getting around a mass spectrum.